Okay, good morning, everyone. I hope you are doing all right. So, we are coming towards the end of this application of laws of motion in rotational motion. Okay, so of course, basic laws of physics we already learned about. They were like kinematics, laws of motion, or dynamics, and conservation principles. After finishing that, we started using all of them in the rotation of an object, rotational motion of an object, right? Something like that. So last week, we learned that, okay, for translational motion, when object moves from one point to another point, it's a force that is relevant. But for rotational motion, it's not just the force, but also where the force is acting, how far, and what direction. By bundling them, we define a quantity called torque. So we learn how to calculate torque by using different methods. And then we learn the kinematics and the equilibrium condition, okay, for the rotational motion, and also the dynamics. So kinematics, dynamics covered, okay, already for this. So now we are talking about moving towards the energy and momentum and their conservation principles. Okay, so just like we did for the translational motion, we said, okay, we need to first, define work, because work is the work is a way of transferring energy. So if we can calculate how much work is being done on the system, or how much work the system does on something, that means we can tell how much energy is being transferred. Okay. So just like we did for the translational motion, we'll start by defining the work done, writing the equation of work done for rotational motion, slightly modification for the rotational motion, and then we're going to write the kinetic energy. Okay. And then we'll learn how to use conservation of energy for rotational motion. Okay, so let's get started. So here, what you see is there is this wheel that's spinning really fast. And now, when you bring it in contact to that surface, what happens? Now the friction acts and friction does the work. And because of that, what happens is the amount of work done by friction gets out as a sound energy, heat energy, light energy, and so on. Okay, so since the friction is doing work, what is happening is energy is getting out from the system rather than providing to the system. And of course, there is electric force that's doing work that keeps that thing moving. Okay, so energy is being put in, energy is being taken out from the system. So energy is still conserved. So how much energy is coming out? How do we find that out? By finding the work done by the force, right? In this case, friction force. So now let's get to a bit general situation when something is rotating. Oh, that looks like a potato. Anyway, so something is rotating here. So initially, let's say the object, we start pushing, let's say. So for example, we are applying force here, which is perpendicular to the radius. Okay, so that means radius is same as lever arm here. So we are applying force, and that force make this wheel spin, right? So it's like a merry-go-round where you push on one side, what happens? The round starts spinning. So that means that point here kind of displaces, and that displacement is written in this case, since it is like arc situation, we are denoting that by S. Actually, I copied this picture from one of textbook. I did not make this picture. So I'm using the notation that was in the picture right there. Okay, so this arc length, and we have used this before. So there is force acting, and displacement is also taking place in the same direction for that, small time interval. So force and displacement are in same direction. Let's say S or D. So when they are in same direction, angle between them is 0 degree. And since the work done is force times displacement times cosine of angle between them, in this case, cosine 0 degree makes 1. So the work done is simply F times D. So for this kind of situation, I'm writing something like this. So you don't see cosine theta there because theta is 0 degree. So this is force times displacement. So whatever forces are acting on that, we want to just make sure that we are including that. Now, this is work done by all the forces acting in an object, let's say. So for rotational motion is the torque that matters. And we know torque is lever arm times force. And in this case, lever arm is simply equal to R, and force is, let's say, F net. So to get the torque from force, what we need is we need to multiply that force by the R. So let's do that. But to keep things equation equal on both sides, when I multiply on the top by R, I need to also divide that by the, I need to divide that expression by the R as well, so that I haven't changed the actual values or anything like that. So the equal sign is still holds, the equation is still holds, but now I have R over here that's multiplying force, so that gives me torque. Another thing I have is this S over R, okay? And then we learn that this delta theta, arc length, and R, they are related by this equation. Delta theta is S over R. And by the way, this theta is not same as this theta, okay? So keep that in mind. So this delta theta is S over R, which is angular displacement when this wheel goes from this point on the wheel goes from here to here during that rotation process, okay? So the angular displacement is delta theta. So I can write this in terms of angular displacement. Hey, work done is force times displacement. So even for the rotational case, it's equivalent. You see that? So torque is the force counterpart, and this is the displacement basically for the rotational case. So still work done is force times displacement, okay? But for rotational situation. So that's the work done. Now, we want to go from work done to energy. Remember, net work done by a force was equal to change in kinetic energy, or half mvf squared minus half mpi squared for the translational motion. Now we want similar equation. So we want to get rid of this displacement. We want to get rid of torque. We want mass and we want speed. So this delta theta or displacement is related to the speed with the kinematic equation. And similarly, mass and torque, so instead of mass is going to be rotational inertia in this case, because that's the rotational equivalent, right? So rotational inertia and torque are related. So we know that through the Newton's second law for rotational case. So we want to replace this net torque by I, and we want to get rid of this delta theta by somehow V, but we cannot just replace delta theta by V because delta theta is not equal to V. Delta theta is related to V through this equation. So that's what we want to write. So V means in this case angular speed. So that's why you see this. Okay. So now I want to just extract delta theta and plug that thing in there or replace by the expression over there. So because of that, what I'm going to do is I'm going to rearrange this, move this to the side of final squared, and then that becomes negative, and then divide that whole thing by 2 times alpha. That's going to give me delta theta. So that is what I am doing here. Okay. So now I have delta theta in terms of speedy square. Hey, that looks like a speedy square. That's great. So all we need to do next is to get rid of this torque to get the rotational inertia using this equation. And that's what I'm writing here. That's what I'm writing here. So now replace this net torque. So W net here, what happens? So we have this W net here. Replace this torque net or net torque by I times alpha. And then replace delta theta by this thingy over there. Okay. And you can see there is 2 times alpha in the denominator over here, right? So this alpha here and alpha here cancels, and there is 2, there is I, hey, there was 2 for the translational case in the denominator or half, right? Same thing here. So we are getting the same, or I should say similar equation, and that's what I'm writing here, okay? So now if I open this, so this is final kinetic energy, and this is initial kinetic energy. But these kinetic energies are for the object that's rotating or spinning, okay? So this kinetic energy is when, remember the translational kinetic energy, when object moves from one place to another place, right? And there is this kinetic energy when object is just spinning in a place. But there can be this combined motion. For example, I have a handy wheel over here. So the motion, this kind of motion we call rolling. So it's moving from one place to another place. At the same time, it's also spinning. So when something is rolling, it's translating plus rotating. So in that case, we have both kinds of kinetic energies. And so that means we have, so we need to differentiate that. And that's what we are doing. We're going to say, okay, this is the final translational kinetic energy, not translational, but rotational in this case, rotational final and rotational initial. So we have 2 kinds of kinetic energies. One is rotational. So what's the formula for that? Hey, it looks like half mb squared. So m and I, they are, I is rotational counterpart of mass. And these are also counterparts. So they are equivalent basically. So what is kinetic energy? Mass times velocity squared. Now we can have 2 kinds of kinetic energy. One, our good old half mv squared, which we call translational kinetic energy. And another one is rotational. So when we say, okay, what's the kinetic energy of rolling object? Then we need to add both of them. Sometimes we may say, okay, total kinetic energy, but we don't have to. Whenever we are, we are looking for kinetic energy, we need to look at both possible kinetic energy. Which one which one does exist here? Or do the both kinetic energies exist in this kind of situation? And If object is not spinning, just moving from one place to another place, that means that is translational kinetic energy. In that case, there is no rotational kinetic energy. But another example, if object is just spinning in a place, okay? For example, you lifted let's say the backside of the bicycle and then just turning the wheel. That means wheel is spinning, but bicycle is not moving. That means that's just the rotational kinetic energy of the wheel. But when you are riding on the bike, wheel is spinning at the same time, so also moving. So that's what we call rolling. When it's rolling, we have both kinds of kinetic energies. Okay. So when something is rolling, it has angular speed at the same time translational speed. And remember the center of mass. So the center of mass of the object basically is moving. That's translating. So if we follow center of mass or the speed of the center of mass, that gives us translational speed. So that's why sometimes in some book you may also see it's written as a speed, mass of, speed of the center of mass of the object. Okay. Okay, so now remember now, kinetic energy means two possible kinetic energies. One translational, another one rotational. Okay, so now with that said, I have a question for you. Let's see, did I start clicker? Looks like I haven't started clicker, so let me start clicker. Meantime, you guys find the answer of this question. So now I'm opening the poll. So their mass, speed, they are same. But last class we learned that rotational inertia of hoop is half, not half, but just mr squared. Rotational inertia of disk is half mr squared. And rotational inertia of sphere is 2/5 or 3/5 mr squared. So that means I hoop is bigger than I disk, and I disk is bigger than I sphere. Right? So that's the things we have learned. So I think it's going to be helpful if you can keep that in your head. Okay, so with that, I'm going to open the poll. And you have a minute to answer this question now. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so let's see what we got. So we got more for B, and D is kind of competing behind, and A is not that far as well. Okay. So let's see. Kinetic energy, we need to write, since these objects, all of them are rolling, we need to write this and this. Okay. So mass is same for all of them. Speed is same for all of them. So this is same for all. The omega, see, R and B same means B is R times omega, or omega is B over R, means when these are same, means omega is also same for all of them. So omega is also same. However, there is this thing called this rotational inertia. So different. So that means difference in kinetic energy comes from just the rotational inertia of each of those. Everything else is equal, right? So in this case, what happens? Rotational inertia is largest for the hoop, means it has the largest kinetic energy. So yes, B is correct answer in this case. Okay. So now let's suppose if there was something not rolling but sliding, let's say, something like that, V and same mass, then in that case, since this is not rolling, there wouldn't be this term here, okay, for this one. So that means kinetic energy would be just half mv squared. So in this case, since it is not rolling, it has a rotational inertia of, let's say, block that's sliding is 0, because if it is not rotating, it does not have rotational inertia. So 0 means it will have the smallest one, okay? So I block sliding, just sliding, okay? Not rotating means rotational inertia is 0. So that means this will have the least one. So that's how the rotational inertia works. If something is rotating, it has rotational inertia. Now, how much? You need to actually look for them, okay? In a book, there are going to be equation for the rotational inertia. If something is not rotating, then it does not have rotational inertia, means rotational inertia is 0, okay? So that's how it works. Now, I have another question for you. So in this case, these are two hoops. Hoop A and hoop B. They are not translating. They are just spinning. So that means their kinetic energy is just half I omega squared. But the thing is, one has, angular speed omega, another one has a double. Similarly, one has radius r, another one has a double of that radius. Okay, so that's what's happening. So do you know what is the I for hoop? So that means kinetic energy going to depend on those I for hoop and the omega. So in this case, you are finding that for A, let's say omega A squared, and you are doing that for B as well. So half IB omega B squared, and then you are comparing them. What is the ratio? Divide this bigger by smaller one. So KB over KA. So these are given directly or indirectly there. So you need to use those to answer this question. Okay. So with that said, I'll let you work on this. So I am giving you 2 minutes to work. On this. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. We got varieties, but there is a majority in B. How do I do it? So first, let me show you how to do it, bit quickly. So since we know both of these are hoops, I can just write this equation something like that for the kinetic energy, right? So now, see, compared to this one to that one are doubling, okay? Double are doubles. Or I should say R doubles. And then similarly, omega doubles. So there is one double coming here on the R in the equation, and another double coming, okay? So R is becoming 2 times R, and omega is becoming 2 times omega for B. But this equation has not just R, but R squared. Remember, the things that are same, for example, mass is same for both hoops, okay? So things that does not change, we don't have to worry too much about it. But the radius is changing, but in this equation, radius is squared. And then similarly, speed is changing, and in the equation, speed is squared. So what do we get here? We get a factor of 4 from that and factor of 4 from the speed. So since these things are multiplying each other, these factors 4 and 4 are gonna multiply as well. So when we multiply 4 and 4, it becomes 16. So that's why when you double these two things, the new kinetic energy becomes 16 times more because those things are square in the equation, okay? So if there was no square, then yes, that would be 2 times 2, right? It would be 4. But remember, they are squared, so that means you need to square the double. So I'm emphasizing this kind of thing, and I have done that in the past as well. So keep that in mind. How that quantity is in the equation. Is it just the R or R squared or R cubed, something like that, right? So any multiple factor that also has to be squared or cubed depending on how the object is. So that's why the correct answer in this case is E. But let's say if I were to do systematically, what would I do? So let's write the Ka. So in this case, I of A gonna be M R squared, right? So that's why Ka would be simply half, and then Ia means MR squared, and then omega A. What is omega A? It is just omega. So omega of A is simply omega in this case. So we write that. So we have Ka. Now let's do same thing for Kb. Okay, kinetic energy of B. So Kb. So before I find that, let's write the rotational inertia. So it is M R squared, but R is 2 times R squared. So it's going to be 4 M r squared. See how the factor of 4 is coming out there. And then now KB going to be IB, which is 4m. Oh, we also need half. Oh, we don't need half. For kinetic energy, we do, right? We have half. And IB is 4m r squared. And then now we need omega B. And omega of B is 2 times omega. So we need that one squared as well. And you can see this is, so I'm keeping half thingy here because there is half here because we are comparing them, right? So whenever possible, we want to keep that in the same shape, but of course you don't have to. So we have 4 coming from here, 4 coming from here. So that's the 16 factor. And then mr squared omega squared. So now you see when you compare KB with KA, everything else cancels, leaving just 16. So let me actually write it out. KB is half times 16 m r squared omega squared, and Ka is half times m r squared omega squared. So now you know why did I leave this half as they are, because it cancels. The things that's not changing, when you take the ratio, it cancels, right? So, and these things here, they cancels, leaving us just the factor of 16. So this is the systematic long way of doing it, but the short and quick way to answer this kind of question is maybe just use that, okay? Short version. Okay, so now we learn about kinetic energy for rotational motion. And potential energy for rotational motion is nothing special. It's just the potential energy. It does not, like matter whether it's spinning or just sitting there. It simply depends on the how high it is from some reference point. So potential, we don't have extra potential energy for rotating object. It's just the kinetic energy. Remember, potential is just the energy due to position, and kinetic is energy due to motion. So spin is a kind of motion, and translation is another kind of motion. So that's why we have 2 kinds of kinetic energies. But potential energy is just a position. Doesn't matter how it's staying there, sitting there, spinning or not spinning, does not matter. So potential energy, we don't have rotational potential energy, okay? With that, so now let's learn how to use conservation of energy, okay? Using conservation of energy to our rolling motion, or we can simply say for rotational motion. So rolling has both translational and rotational, but we can have just simply rotational. We can use the same idea to, for the object that's just rotating as well. So remember, in physics, using conservation of energy is one of the widely used technique to solve problems. So that's what we are doing here right now. Very important stuff. So if you miss that for the translational, that's going to be captured here as well. And especially our midterm is coming next week, right? So it is scheduled for next week. So it's kind of review of the energy concept on how to use energy concept or conservation of energy to solve any problem. So in the past, what we have done for translation is like something here, just sliding here. No rotation, just to be right. So that's what we have done in the past. And when we had that, we said, okay, let's put the initial. Let's mark the final. position. And let's choose a reference point because gravitational potential energy depends on the height. So we need to measure height or vertical position from some reference point. So we need a reference. So that's what we've been doing. Okay. So that's what we are doing here as well. See, it's the same thing. We are just using the idea we already learned. See, the basics we already learned. We're just using them in different kind of situations. So depending on situation, we may have to modify ourselves for the situation, right? When you are going through a door, you can just go nicely with your, hands and so on, setting something like that. No worries, door, regular way to go. But if you have to pass through the window, we have to be a bit careful, and we may have to, uh, you know, let's say reorient ourselves, modify our posture a little bit so that we can get through the window. But it is just passing through door or window, similar process, right? Similarly here, basic physics, kinematics, dynamics, conservation of energy and momentum. Those are basics. And we just use them for different situation. Depending on a situation, we may slightly have to modify them. That's all we are doing. Okay. So in this case, see, the process is same. So object right now is not sliding, rather it's rolling, and it starts from there and then it starts rolling. So it has one kind of motion we call translational motion because it's moving from here to there, to there, to there, to there, right? So that is translational motion. And at the same time, it is also spinning while rolling downhill. So both kinds of motions are there. So this, since we are starting from here, I am labeling that as the initial point. And then we are interested, what is the speed at that point? Okay, so that is our final. And I'm saying, okay, when it arrives here, the speed is v, translational speed, and rotational speed is omega. And I'm choosing this as a reference point. So with that, I can start listing things. Okay, so that's what I have done here. Initial velocity is 0 because it starts rolling from there. And remember, v and omega, they are related. So let's say, what is omega? Omega is p over r. So whenever v is 0, omega also going to be 0, right? So whenever linear speed is 0, angular speed is also 0 when it's rolling. So when it's not rolling, that means it's not moving, it's not spinning as well, okay? So that's why both of these are 0 at the beginning, translational speed and rotational speed. Both of them are zeros. And then initial position, I'm saying whatever the height of this ramp is. Okay, it starts from there. So let's say that is h. And then now, what happens here at the final? So V final is V, and that's what we want. And omega final is omega, let's say. And omega is V over R. So if we know V, then we know omega. Basically, they are related. So I can write like that, omega F. And how about YF? So since it is arriving to the reference line, vertical position or height is 0. So this is 0 here. Okay. So now with that, let's write the conservation of energy. So now, in this case, we are saying, okay, the friction is negligible for rolling motion. So we don't have to worry about energy dissipated due to friction. We are neglecting friction. So that means in this case, there are only two kinds of energies, kinetic and potential, which collectively known as mechanical energies, right? So it's just mechanical energy. So kinetic energy and potential energy. So total energy is kinetic and potential. And we learned that there are two possible kinetic energies, translational and rotational. Okay. And so far, we also have learned two types of potential energy. One, gravitational potential energy that depends on mass and position. Another one is elastic potential energy. So elastic potential energy comes in effect only when there is something is being stretched or compressed. Here, that kind of thing is not happening. Or stretch or compression. So that kind of thing is not happening here. That means we don't have to worry about it. Okay. So now I'm going to write these three kind of energy. So this is also called gravitational potential energy. So that's what I'm writing here. So I'm writing them in details with initial and final. So these two are our good old, we used to have just kinetic energy. Now we have two kinds of kinetic energies here. So we are writing both. And this is gravitational potential energy. So for the final side, we have final as a subscript. Okay. And we just copy them on that side. So now we can expand them. Okay. So for example, this is half mvf squared. This is half I omega squared. And this is mgyf. And this is half. It's just like that, but with initial subscript. And this is half I omega I squared. And this is mgyi. So those are the things here. Yeah, you can write them all in details. But here there are a lot of zeros. So vi is 0 means this term here gonna be 0. Omega I is 0 means this rotational kinetic energy is also 0 at the beginning. Only energy it has at the beginning is this one here, gravitational potential energy, because of its height from the reference line. On the final side, when it arrives here, height is now 0 means this is 0, final 0 here means this term is 0. Okay. But these are non-zero terms because it is rolling, means it is spinning and translating when it arrives here. And after that, yes, it's going to be rolling, but we're not interested after that point. Okay. So this is our final point because we want with what speed it arrives to this end of the slide or inclined place. Okay. So that's what we are doing here. So I think that's what I am showing here in bit short without writing those details. So now with that, let's expand these three remaining terms. This one is that, this one is that, and this one is that. Yi is h. Remember here, so that's what I'm writing. And I'm saying v final is just v, okay? And omega final is just omega, because initial they are not there, so I don't need to differentiate them. So I'm just writing them without subscript, from now on, because we don't have initial and final v. So I can just write V for final. Initial is 0. So that's why that one is not in this equation. So now we want V, but we just learned that omega also has a B in it. See, this also has a B in it. So we cannot just solve for this B and say, hey, we are done. There is B here hiding, okay? So we need to show it. And now this rotational inertia, let's talk a little bit about rotational inertia. So we already learned that rotational inertia for the hoop, rolling object, what are the possible rolling object? One is hoop, another one is disk, and another one is sphere. So let's write all of these rotational inertia, mr square, assuming their mass and radius are same for now, okay? I for the disk, half mr square, and I for the sphere. And there are two kinds of sphere, solid and the hollow. Hollow has 3/5 and solid has 2/5 mr square. So pay attention, all of these have mr square on this. The object that can roll, all of them have mr square in their rotational inertia. And so that means what differentiate the rotational inertia among these? So it is just one thing, that is the numbers in front of, let's say this is 1 mr square, half, 2/5, and so on. Only that number in front of that mr square differentiates. So that means I can write just one formula for all of those. And that's what I'm doing here. I'm writing mr square times some number. So what number is that? So beta, I'm saying, is a constant, some number. So when we know this object is hoop, we know beta is 1. See, the number in front of mr square is 1, so beta gonna be 1 for the hoop, and so on. And that's what I'm writing here, okay? So beta is 1 for hoop, beta is half for disk because there is half here, and beta is 2/5 for solid sphere. But for hollow sphere, then it's going to be 3/5, which is still the beta, okay? So that's why rather than writing them as a separate, I'm writing this because, and why am I doing this? Because I don't know what kind of object that's rolling. So I'm trying to come up with the way of doing it, even without knowing whether it is a disk or hoop or sphere. More general situation. So that's what I'm doing here, okay? But let's say if you knew it is a hoop, for example, then you can replace this I by just mr square if it is a hoop. And if it is just a disk, if you know, then you can replace that by half mr square and so on, okay? But for now, let's say I don't know what this rolling object is. So I want to write with more general equation. So now you can see why I am writing the way I'm writing this rotational inertia. See now this r square cancels. And what is r? R is the radius of rolling object. So r canceled. What that means? Let's say if it is a hoop, whether it is a big hoop or small hoop does not matter. Okay? As long as we know hoop, how big the hoop is does not matter. That's what it is saying when we cancel r square. Okay? And similarly, the mass here, mass here, mass here, they cancel as well. So if I did not write like that, See, I could not see those canceling, okay, for all these objects. So that means as long as we know hoop, it doesn't matter whether it's a bigger hoop or a smaller hoop. Similarly, as long as we know hoop, it does not matter whether it has a more mass or a smaller mass. That's what it is saying by canceling the mass in this equation. Okay. So after I cancel those, I am left with this. So now you see there is b square here and b square here, and I want to solve for b. So that means I need b in one place. But right now they are in two places. So what I can do is I can basically factor b square. So when I'm factoring b square, I see there is half, there is half. So maybe I can factor that one as well. So I factor this whole thing. I'm left with not 0, but 1. Okay. So 1 times b square, half b square is half b square. So I haven't changed anything. I just rearranged that. Okay. And there half is gone, b square is gone outside the parenthesis, means inside the parenthesis we have just beta. So that becomes 2, or just g times h. Okay. So if I bring this 2 from the denominator here, it's going to be 2gh. And now to solve for b square, I can move this 1 plus beta. And 1 plus beta is multiplying the b square. So that means when it goes to the other side, it's going to divide. And that would be b squared. So to get b from b squared, we need to take square root. So that's the equation for b. So if the height is known, for example, let's say if that number is known 2 meters, you can plug in that 2 meters here. And if you know the shape is, let's say hoop, then you replace this beta by 1. If you know shape is disk, you replace this beta by half. And similarly, if you know it is a sphere, that you can replace that by 2/5 or 3/5, depending on what kind of sphere it is. Okay, so that is velocity. So now, if something is being rolled from a particular inclined plane, top of the inclined plane, what happens is height is fixed. And of course, we know g is fixed. So that means how fast one arrives just simply depends on beta. And b and beta, they are inversely related. It's not direct inverse relationship, but just some sort of inverse relationship. What that means? When beta is, let's say, smaller, b becomes larger. The one that has a b beta is smaller, b is larger. By how much? We cannot tell just by looking at that equation. For that, we need to actually plug in numbers and find out. But even without doing that, we can tell how they are related. So that's the beauty of writing equations, something like that. So give me a shape, and I'll tell you which one gonna arrive faster here, or will they arrive together, or something like that. Okay. So B is beta dependent only. Okay. So a smaller beta rolls faster. So that's what I'm writing here. Now, here you see there is a disc, wooden disc, and there is a hoop, metal hoop. Okay. And if you like, you can say they have same mass. Okay. So now, which wins the race? So I'm going to make a clicker question. So you need to tell me based on what we just talked about. So A, hoop, B, disc, C, let's say tie. Okay, so this is question. So you want to predict based on what we just talked about. So for your convenience, I'm saying, okay, let's say they have same mass. Okay. And you can see size is also same. They have same radius. So I'm going to poll before I run this. And you have 30 seconds to respond. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got here. So basically, disk a little bit more, but hoop and disk looks like competing. And there is also some tie thingy. So now let's watch this video. And after watching this video, we're gonna take a break. So sometimes, since this video is from YouTube, YouTube may complain I'm planning to post this one. So it may complain. So because of that, I'm gonna pause the recording. Okay. So when we come back from the break, hopefully I will start recording, but if you notice I did not, then let me know so that I can. So first I'll show you, how to quickly answer this question. So both of them have kinetic energy, but hoop has higher kinetic energy. Why? Because kinetic energy means half mv squared. So this is same for both, but half I omega squared. See, this is larger for hoop. Okay, so that means hoop has higher kinetic energy. So that means it will have higher potential energy. Why? Because energy is conserved. So whichever has initially maximum, the finally that will have the maximum as well at the maximum height. So since tensile energy higher means, see, mass is same for both. So that means Y is larger. Should I say YF in this case? YF is larger. So that's why hoop goes to the greatest height on the incline. Okay. But we can also do mathematically just like we did before. Okay. And so let's set up this problem here. So this is the initial. So this is just for one object. We'll do this for one object. I think here I'm saying disk, but it can be replaced by hoop as well. It's simply a matter of rotational inertia difference, right? Otherwise, everything is same. So this is the initial. So how high it reaches? So we want to know, let's say if this is a reference. Let's say it reaches somewhere before it starts turning around. So that's the maximum height it's going to be. So YF is H. That's what we want. Okay. So at that point, BF going to be 0. And so is the omega F because it briefly stops before it starts rolling back again, right? So initial VI is V, omega I is V over R, because omega is V over R, right? V is R times omega. And then YI is 0 in this case, okay? So total final energy is total initial energy. And because this is disk, it has rotational inertia of half mr square for the disk, right? So that's what we know. So kinetic energy, two kinds of kinetic energy. And one potential energy. And we repeat that for the initial side. Okay, so that is how far I went. So now how about you go ahead and find the V. You do the remaining, okay? And once you have the equation for V, type that on the chat, okay? Everyone, please do it. Maybe this question will be on the test. Who knows? You know, chance to practice algebra and this one. Redo this problem using hoop and redo it using sphere, okay? See if you can come up with simple answer like this. Okay? Now, so this is the energy and conservation of energy. Now let's move to momentum. So for that, I have this video. Again, I may have to stop recording here. So by bringing hand, like from the straight position to straight line like this, what's happening is the final rotational inertia is larger than this initial rotational inertia, okay? So changing the rotational inertia, and that is changing the angular speed. So how inertia and angular speed are related? One is kinetic energy, but we can also think in terms of momentum. And notice how this is done in ice, not on the carpet. You cannot do it on the carpet, okay? So we are describing this phenomenon or explaining that phenomenon in terms of angular momentum. And notation for angular momentum is uppercase I. And just like momentum is mass times velocity, this is, see, the rotational counterpart of mass is rotational inertia, and V is same, counterpart of the linear velocity is angular velocity. So that's why that is angular momentum. And L kind of reminds us that it is angular. It looks like an angle here, right? So that's a good notation, I think. So now just like linear momentum is conserved, angular momentum is also conserved. So what that means, total final angular momentum is equal to total initial angular momentum, provided that the net torque acting on the object is 0. So that's why it has to be done on the ice. Otherwise, on the carpet, there are going to be friction and length of that foot. That's going to be like lever arm. So friction and lever arm going to give you the torque. So that is external torque, means the angular momentum not going to conserve. Okay. So when net torque is 0, we can write something like that. And then since here we have just only one person, right? So there are no two masses like in the collision. Here is just one person. So I can just write final and initial, something like this. So it's simplest form. So product of rotational inertia and angular velocity is the angular momentum. So we can do that for final and initial, right? And remember, rotational inertia is sum of all these. So that's why R larger means I larger, right? And that's why, oops, now I messed it up, looks like. So I'm going to briefly exit from here. So you see here, oh, angular momentum. So R for that mass is there, right? And that mass is there. It is also tilted. But over here is straight and axis of rotation is here. So all the masses are kind of closer. So that's why omega is increasing. So if I were to rewrite this equation, what's going to happen? Let's say omega F is I omega I, divide that by IF. So IF smaller denominator means this is larger. So that's why spin rate increases by just bringing the body parts, close to your body or axis of rotation in this case. Okay, R is measured from axis of rotation, you know that. Okay, so now I have a question for you. Oh, you have a minute and 30 seconds. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. So mostly B. So yes, so that is correct answer, just like we talked in previous slide. So angular velocity increased because rotational inertia decreased, right? So that's what we said here. Final become smaller, so that become larger. And there is a kind of problem with numbers, okay? The same situation. So they starts with their arms and leg fully extended and then brings them closer to body, changing rotational inertia in the process. What is the final angular speed? So omega f is what? If the initial angular speed is this, so that means omega I is 2 radian per second, and rotational inertia for kilogram meter square. Remember, rotational inertia is mr square, so the unit is kilogram for the mass, and the unit for the distance is meter, so meter square. So that's why the unit like that. So it says assume the final rotational inertia is this, so IF is 1 kilogram meter square. So this is angular momentum part. So go ahead and calculate the value of omega f. In this case, numbers are fairly simple, so you don't even need calculator or anything like that. So go ahead, do that. Is energy conserved in this case? So did anyone find the final angular speed? If you did, type that on the chat. So on the second part of this question, it is asking to see if the energy conserved. So that means if it is conserved, then this should be equal final and initial. So you need to actually calculate these values, and all these numbers are there. Calculate them and compare them, okay? So and that you should be able to do it. And so far we focused on the values, but all these quantities, angular momentum, torque, and angular speed, they are vector quantities and they have real physical direction, okay? So for the torque, we said, okay, positive and negative for counterclockwise versus clockwise, right? but that is not actual physical reduction. So how do you find physical reduction? So for that, you need to use what's called right-hand rule, okay? So those things, the actual physical reduction of these quantities and what's the consequence and so on. So I have some videos on the slide, so I'll show those videos and talk about them in next class. But today I'll just leave it here. I think it's a good time to leave it. And then after that, we're not going to be introducing new materials. So looks like after that, we're going to do some review starting from the uh, circular motion. So your second midterm going to start from circular motion and go all the way up to here, okay? Uh, but of course, the kinematics, dynamics, those things we have learned, they are relevant in this case as well, but they're not going to be directly tested for the midterm too. But final will be comprehensive. And I thought it's going to be on Tuesday next week, but the way I have written in syllabus, it is on Thursday. So midterm 2 is on Thursday next week. I need to double check syllabus, and I think that's how it is. But whenever it's written in syllabus, okay, or in syllabus, I cannot change that. I have to stick with syllabus. So I think it is on Thursday next week. But I haven't looked at recently, so I have to double check. Otherwise, that's going to be the case. Whatever is in the syllabus. So check syllabus. Okay, folks. So for